that close enough? Okay. So we'll go with the word of the day, gregarious. Anyone know what that means? Isn't that like outgoing or something? Or? Okay. Something interesting. We'll try this again. I've got a little bit different setup, so I've been in here for about an hour playing with things, and hopefully the technology will work a little bit better. So this is live streaming now, which means it'll be available right as soon as we're done. I'll put the link into Canvas, but if you go to my YouTube account, which is, if you go to YouTube, the channel name, it's two N's, isn't it? Channel is Open Global Village, all is one word. I'll just run together. So if you just do a search on that, it'll come up with plus a lot of other YouTube sites that you're welcome to check out, I guess. But and actually, the link to it is already in Canvas. So if you go there, what I do is I'll keep a playlist of all these videos, so you'll be able to look back at them through time. So whatever's at the top of the playlist is the last video of class. Okay, and then the previous videos will be there. Last week's video did not work out so well. Like, there was a file on my disk, but it wasn't playable. So we'll do a little bit of review for any questions that you might have. If you still have any questions on 10.1 or 10.2, you can send me an email and I'll make a small video or something. I didn't. This first 2 weeks of classes have been busy for me, taking care of some issues. So, but anyway, 10.1 and 10.2. Any questions, just let me know. I've also extended the due dates on all the assignments so that you get at least 1 week in between when we talk about it and when it's due. There was I had a lot of them set to be due on Friday, because I gave at least one more class day. So we'll go over like today's stuff. You've got Thursday to go over it, but some of you are working, so maybe you need that weekend. So I just moved them a couple days. So the Friday ones, the ones that were due Friday, will be due Monday. There's no late penalty, although the way the system works, if you are past the due date, it won't let you in. Email me, I can open them back up. But I wanted those due dates to try to keep you on track as much as possible, and trying to give enough lag time that it shouldn't get you too much. But if you do, don't worry, there's no penalty. Just let me know you need to have it opened up again. Okay. What else? Questions from... No questions. Good. See, most of you are making some pretty good progress. I looked, I think Friday it was, or maybe it was over the weekend. Anyone who hadn't finished the first part, I put an extension at least through till next Wednesday. So those should be all open. We will actually be finishing up chapter 10 this Thursday, which then means I'll also have a practice test for you, and then we'll also have a test, our first online test, and we'll see how that works. Again, I'll hopefully before Thursday be able to do some kind of a practice run of how the online proctoring works, and anyone who can give that a try, that will be helpful, and then we can see what adjustments we might need to make on Thursday. But then the goal will be that Thursday I'll also, after we finish class, give you a practice test, and then the following week there'll be about a week's time for you to take the test online, and again it'll be proctored through Respondus browser, lockdown browser, and hopefully we'll be able to get that to work for everybody. Yes?
So for the test we'll have like all of next week to work on.
Yeah. Yeah, we'll especially if there's any technical things. We'll work it all out. Again, my goal is that you work through the stuff and you get some understanding, and that if there's some technical issues or time issues, we just kind of work around those and keep moving forward. Okay, good. So let's do that. Okay. So tonight we're looking first at 10.3, which is going to bring together limits and continuity. .1 was about limits, 10.2 was about continuity, so 10.3 must be put the two things together. And it pretty much is. However, we'll also take a look at things algebraically in 10.3. Okay, which 10.1, when we were looking at limits, we were using mostly numerical. So we used the graphing calculator to look at what happened as we got close to a particular point, a particular x value. We were looking what kind of y value is there when we get close to an x value. That was the concept of limit, right? Seem about okay, good. Continuity, what was sort of our general definition of continuity? How could we tell if something was continuous? What's the simplest way to...
You have to raise your hand off.
Okay, if you had to raise your hand off the paper, it wasn't continuous. If you could draw with one continuous stroke, it was continuous. So it's yes. We used limits, left and right side limits, and something else to determine if something was actually continuous. And there was three conditions that made something continuous. And does anyone remember what those three things were? Actually, maybe it was two things. Well, it was three things. There was a relationship between the three things: the left limit, the right limit, and the actual value.
I think one of them was they have to be equal.
They have to be equal. Is that
The point is the same coming from both sides, and the function value, it exists at that point.
very good? So it was sort of three parts to it, but really, yes, it's really that they're all equal. So the limit as x goes to a of some function coming from the right, and this was a, so this plus mark just means that you're coming from the right. You're maybe coming from the positive direction, but you could interpret it, it could look like, well, we're going towards the positive, but that's not what it means. It means you're actually going from the positive towards it. So this is a right limit. So I'll just put this down here as a limit from the right. Okay, that has to be equal to the limit.
So, like, because you're backwards. So, going from positive to negative.
Right, that's correct. Yeah, so coming from the right-hand direction. Make sense? And then we also have that the limit going to that same value, if we come from the left, come from the negative towards the positive, just, yeah, okay, that is equal, that the limits are equal of f of x. So we call this and that it's that if it is also that the function value at that point, that value a, as we plug that in for x, that y value is the same, if all three of these are the same, then it's continuous. So that was the mathematical definition of continuous. Okay. What we're going to do today is we're going to start off talking about functions that have this quality, so we know they're continuous. And what it's going to allow us to do is algebraically just find the limit without doing too much dancing around this concept of numerical or graphical. We're just going to plug it into the function, and we're going to be able to find the limit that way. So it'll seem very easy, but it's based on all that mathematical theory we were building on. And that's really what this first chapter is about. It's about the math theory that allows us to do a lot of the other stuff that we're going to do in 11 in a lot easier form, a lot more elegant. Okay, so what we're able to say, if all this is true, if we know something's continuous, then we're simply able to say, well, the limit from the left and the right are going to be the same, so if the limit as x goes to a of f of x, let's see, then it's simply going to be equal to f of a. So the simple example they give in the book is they start off with a real simple one, like x going to 3, and the function is something like x plus 2. And so how could we evaluate that to find that limit without having to put it in our calculator, find out what's happening at 2.999 and what's happening at 3.001? If we knew this was continuous, what could we just do? Well, we know it's going to be equal to the function at 3. So let's just plug in 3 for x. Say that the limit has to be 5. So just the algebra, plug it in, calculate it, we're done. Okay, again, but it was all this theory that allowed us to get there. So far, so good? So I say, this class actually gets easier as we go, because we go from theory of painstakingly proving that these things happen to, and exploring, to then saying, well, if this happens, let's just plug it in and move forward. Okay. So the next step is we start talking about functions that have what we call closed form. And this is all in the textbook, so if if you open up WebAssign, go to the ebook, this stuff will be in there, a little bit more wordy than maybe I'm doing, but I'll try to give an overview. We'll look at some applications by looking at some actual problems, and hopefully that'll help us to understand what they're all talking about. Again, remembering a lot of this is vocabulary, theory, and probably stuff you'd need to know if you were going to be a mathematician. But if you're not going to be a mathematician, you just need to be able to apply it for the most part. Okay, so closed form simply means that we have a function that's a combination and you might read this. I'm going to give the example. It's a combination of constants. What's a constant? Something that doesn't change. So it could be a number like 2, 3, pi. Pi is a constant, so it's a number. Or powers of x. What's a power of x look like? Good. It's x with an exponent. Various exponents. Okay, good to have a coefficient in front. So basically any polynomial is a closed form function. And it gives a lot of things. Basically, just about everything we're going to deal with. Exponentials. So that's a constant raised to a variable power. 2 to the x, e to the x. And you'll use this a lot in business because e is the natural number. So it's we see it with finance. So these kind of functions, radicals, which is our square root functions. Again, on their domain. So some of these have a limited domain, but on their domain they are called closed form. And we're going to see closed form functions are continuous. So that's kind of cool. So if we know we've got a closed form function, we know it's continuous. So on its domain, we're just going to be able to find the limit by plugging in the function values. Okay, a couple other logarithms, trigonometric trig functions, which we won't be working with anyway, so we'll leave those off. But pretty much everything else, the only thing that's not a closed form function that we might deal with are the piecewise. Let's see. So I before E, it's PEI, isn't it? Yes?
Yeah.
Okay. PEI.
Oh, you had it
Oh,
right.
I had it right. See,
Yeah.
those I and E's always mix me up, and even when I get it right, I feel like it
I before E and something.
after C. And then it's all those exceptions that I mess up on. So piecewise. And the reason piecewise aren't closed form, you might have something like x minus 1, but that's for x less than 0. And then maybe when x is greater than 0, you have a different function like x squared plus 9. And they might not meet up at that change-off place. And we saw that some of these were the ones we were looking at. If they don't meet up at that where the domains change, then actually one of these has to be equal, right? So we'll go there. If they don't meet up, then it's not continuous at that point. So these are, if we looked at them as two separate functions, each one individually is a closed form function, but when we put them together and make them into one function, they are not closed form because there's that one place where x equals 0 where they switch from one function to the other, and they might not be holding hands. If you want to picture like that. Okay, so piecewise functions we're going to have to kind of deal with separately. We're going to have to take a look and see what happens at that boundary point where they change from one function to the other. If they do match up and have the same value, then it could be continuous, but everything else will be fine. Okay. So then what we're going to spend our time doing is we're going to look at something. Let's see, this is similar to one in the book, but I made it a little bit different. So we're going to take the limit as x goes to 3, or actually negative 3. And notice the negative is in front, so this is not going to 3 from the left, it's negative 3. Okay, so this is, just have to get used to math. It's really technical. A symbol in a slightly different place means a completely different thing. So this is as x goes to negative 3, both from the left and the right. And the function we're going to take a look at is x squared minus 9 divided by x plus 3. Now, can we just, is this a closed form function? It is. It's one that I didn't mention. Rational functions actually are closed form functions. It's on its domain. So it is continuous on its domain. But is there a point of x, is there a value of x that is not in that domain? Is there a problem child up there? When you're looking rational functions, what's that?
Negative 3.
Negative 3. I almost couldn't pick it out because of the limit, right? what happens when we put negative 3 in for x? The denominator is 0 and the world blows up. It goes to infinity, or it becomes undefined, however you want to look at it. That's, yeah, mathematically, that's a problematic thing. So x equal to negative 3 is actually not in that domain for the rationals. So it is a closed form, but we're dealing with something that is actually not in the domain. So if we want to find this limit, can we do it algebraically? Well, there's another whole theorem, and again, we'll look at it afterwards. This kind of leads us into it. It's the fact that if functions have equal limits and they have the same values everywhere except for maybe at one point, then they're going to have the same function value at that one point that one doesn't exist. So let me explain what that means. With these ones that are going to be in this section, what you're going to want to do is you're going to want to factor, because all of these will suggest the only way you really can do it, can the top be factored into something? And this may be thinking back to college algebra, and we don't do a lot of factoring anymore these days, but if I said that x squared minus 9 is a difference of squares, would you believe me if I said it factors into x plus 3 times x minus 3? Okay, so this is one of those sections where we will needing to do a little bit of factoring. Okay, and then in the bottom it's just x plus 3. And I'm being a little bit sloppy here, maybe a lot of sloppy, because I haven't carried the limit over, but I'm just kind of doing some side work, let's call it that. So, what do you know about x plus 3 and x plus 3? Cancel, because we're multiplying that these will give us the same value, so it's like, yeah, they cancel out. So this function really is going to behave like the function x minus 3 everywhere. Except x minus 3, could we have plugged in negative 3 for that function? This red function here, do we have any problem if we put in negative 3 for x? No, we get negative 6. But the original function, we get negative 6 on the top, but we get negative 6 divided by 0, and that causes the problem. So again, some math theory says that, well, since this function and this function are the same, let's call this f of x, we'll call this g of x. Since these two functions, f of x and g of x, are actually equal, the outputs are equal everywhere except that one place, that actually the limit will be equal. Doesn't say the function value is, but that the limit at that place for f of x will be equal to the limit of g of x. So what it does, it allows us to do this little canceling trick, get a function that's basically the same thing except at that one place, and then evaluate g of x at negative 3, plug that in, and we find out that g of negative 3 ends up being negative 6. And so the answer to this, the limit, we're going to also say will be negative 6. Okay. So this time we're doing it algebraically. Last week we took a look at this and we did it numerically. And we saw that using a table of values, as we got closer and closer to something like negative 3, we got closer and closer on both sides to negative 6. Okay, so what we did last week sets us up to say that, yeah, this makes sense. Numerically it works, and now we've got sort of a theory that says algebraically it works okay too. Okay. Again, since most of us are not mathematicians, we don't care so much about having it to work, But it's just like having lawyers. We may not want to get into all the work of lawyers, but if we're doing something with a business or whatever, we want to make sure it's legal. We want to make sure we've got our copyrights in place, and so we hire those people to take care of all of that for us. So that's what the mathematicians did. They made sure that this really does work all the time, and that we're not going to get caught that on Tuesday of a full moon it all of a sudden doesn't work. Okay. So far so good. Yes.
So the one that didn't have any of that kind of equations, so we have like all the ones that we just have to plug into the limit.
Really?
Yeah.
In 10.3?
Yeah, all of it.
We'll take a look. Last week I thought a couple of them required the factoring. Maybe only one of them. Maybe you got lucky and got because it does do a random problem. So you might have got one that didn't have to do something like this. But I was in the right place. I think there is one or two, because they almost stumped me. I said, what are they doing here? Yes. If they ask you to do, in this one, if they ask you to do it and you've got a rational, it's really the only way we have to do it is with this factoring. We'll take a look at it.
0 over 0. We're plugging in negative 3.
Okay. On which one?
This
On this one? Here. Yeah, so that would give you at the beginning a negative 3, give you a 0 over 0. In math, we call that an indeterminate form. And so, because it really tells you it's not 0, it's not infinity. So that's why we can work with it. If we factor it, then we get part of it to cancel out, and we'll see that the limit actually ends up being negative 6. But right, if we just plug it in, we can't do that here because it's actually not part of the domain. And right, if you plug it in the original function, 0 over 0, and it doesn't tell us anything. Yes?
So if you were to read this word for word with like the solution found, you would say like the limit as x approaches negative 3 from both sides.
Yes.
Is negative 6.
Yes.
So that limit, since it's negative 6, does that mean like that's where it's not? What exactly does it mean that it's the limit?
Okay, good. So what it's saying is that at the point when x is negative 3, whatever this graph is doing, and I'm not quite sure I know what it's doing, but when it gets to, let's say here's negative 6, that there's going to be this point, and it's actually going to be an open circle because it's not, negative 3 is not part of the domain, and that what's happening is that the function on both sides, and again I don't know what it looks like, but I know that on both sides, it's when I follow those lines, both sides are going towards negative 6. That's what it means.
That's where it's like discontinuous.
And it's discontinuous at that point because it's not in the domain. It doesn't actually exist.
So that's what makes it the limit.
Yes. Yes, that's where we have to have the limit, is when we've got that point, that hole in the graph. That's the only way to think of it as a limit. If there wasn't that hole, then we just think of plug it in and we get the function value.
Okay.
But the limit we use to analyze something where basically there's a hole and we have to figure, well, if I was driving down that road, if I maybe went fast enough, I would go over, it would just be a pothole and I'd be okay.
All right.
So it allows us to deal with data that we don't have or data that doesn't exist. And again, as long as coming from the left and the right, it's the same, then we do have that limit will exist. If the limits are different, then you don't want to deal with it because that means that the limit from both sides doesn't exist. The limit doesn't exist. So sometimes we'd have a left side limit and a right side limit. If they're not the same, we just drop that one. Don't want to deal with it. But if they are the same, then we can say, okay, we're in the same neighborhood, we would come upon it. And we can do that if we had just sort of one missing point. Because remember, a point is very, very small, really. very small. Because points don't actually even take up space, so it's what is a point? So, okay. So we'll take a few looks, and that leads us into a couple of general principles that we could use basically to solve everything. But I'm going to talk about 3 cases on one more concept. So instead of looking at the limit when we go to a point, we want to see what is the limit of something as x gets either really big, so it goes towards positive infinity, or goes towards negative infinity. So that's another thing. So we're going to look at the limit as x goes towards, and they'll put the plus here to indicate that it's positive infinity or negative infinity. And so we'll look at something like, and I know there's a few of these type of in there, so okay. Now if you've had college algebra, you've probably dealt with these. You dealt with them without limits, possibly without thinking about limits. But what the question is as x gets really, really big, what do we need to look at? And from the experience you had with looking at the tables of values, hopefully, you saw that when we have a polynomial, what really determines things is that the largest power of x. So in this case, x squared and x squared in the bottom, these are the biggest one in the top and the biggest one in the bottom, are going to determine how this function behaves. And so we take a sort of a shortcut that really all we have to look at is what happens to 2x squared over x squared. So notice I'm just not paying attention to the -1. I'm not paying attention to the -4x. If I were going to graph these things, I would need those. And in the short range, those things are important. If I was looking at the limit, like say between -10 and 10, or in the close range. But when x gets really big, those are just small potatoes. Okay, so I just kind of look at this, and so now this has sort of simplified it. And what can I do here? Can I simplify this further? What's x squared divided by x squared? 1. So it's, yes, when they're, again, as x gets closer and closer to infinity, these both get incredibly large, but something really large over something really large, the exact same value, they will cancel each other out. And so what are we left with? 2 over 1, this ratio, or just 2. Okay, so on this case, what we do is we look at just the 2 largest degrees on a polynomial. We take those, ignore everything else, reduce that, and if we get a ratio of just a number, that's what the limit's going to be. And what that looks like on a graph, hopefully we've experienced a few of these. What's happening on the graph is in the long run, if this is 2, wherever it came from is going to kind of have a horizontal asymptote there. It's going to just kind of level off at 2. Maybe from the top, maybe from the bottom. And again, I'm not saying this is what the graph looks like, but way out at infinity, that's what it's going to do. It's going to level out and pretty much just shoot for positive 2. Okay, does that make sense? Okay. So this is another way we look at them. And the good news is when we get to 4, it's about average rate of change, which is a slope. So if you did 1.3, you've actually got more than enough to get through 10.4. So that's going to be a shorter part. Okay. So then there's another thing that could happen, though. We could be looking for the limit as x goes to positive infinity. And let's look at a slightly different one. Let's go with negative x to the third minus 4x. And I think these are examples directly out of the book. I don't think I changed them much, so you could probably see this. So again, what's the parts that we need to pay attention to?
The highest degree.
Highest degrees. So we're just going to look at negative x to the third, 2x squared. Okay, so we just drop everything else out, and then now we're going to analyze this as if it were the function, because when x gets big, this is all we got to worry about. What can we do with x to the third and x squared? We can divide them out, so 2x's go into here, so this is the x squareds are going to cancel out, and we'll just be left with an x to the first in the top. Does that make sense? There's 2 in the bottom, 3 in the top, so 2 of them match up and become 1. So what we're left with is negative x over 2. So as I plug in sort of really big numbers for x, what is this value going to go to? A really big number, I stick a negative on it, so that's going to make it negative, right? Because as I go to positive infinity, I'm getting positive numbers. Positive numbers, you stick a negative on it, and then you divide it by 2. What does dividing by 2 do for you? Makes it smaller, cuts it in half. But if you cut infinity in half, where are you? You're still really big, yeah. So, and against, you know, half of infinity is still infinity. You know, it's this weird conversation we could have, but it's just, there's nothing, you know, you divide it by 2, even if you, no matter what you're dividing it by, it will eventually get towards infinity. But which infinity? Positive infinity or negative infinity? Negative. Because as you plug in a positive value for x, first thing you do is stick a negative on it. So remember that what we're looking at is, remember that the result of the limit is what happens to y. So this is where you have to think. X is going towards positive infinity, y is going towards negative infinity. Okay, so watch your positives and negatives, watch your powers on here, and which direction you're going. So you just kind of, these are all about just kind of reasoning your way through things. But it's to the first power, so I plug in a positive number, it's going to be positive. If my limit, if I was looking what happens as I go towards negative infinity, what would be my answer here? Would be what? Positive infinity. So as x goes towards the negative side, a negative and a negative make it positive, so the y actually goes towards positive infinity. So you just have to kind of reason your way through here with these a few simple arithmetic properties. What's happening when I multiply negatives? Yeah.
So when you look at this,
Mm-hmm.
would you look at, like, what the one is, it's positive, so it's coming from the positive sign, so when you look at the line, but it's going to be a negative infinity.
Right.
coming from
Yeah.
the-
So I would say as x goes out here to positive infinity, y is going to go down to negative infinity. Yeah. Yeah. So yeah, we're going to go here, here, and so as x is going to positive infinity, whatever's happening, you know, I'm moving along this way. The function itself actually goes down to negative infinity somehow. Okay, so it just keeps going down. Okay, one more case. What do you think that one's going to be? So we had the same degree, we had a bigger degree in the top and then the bottom. So the third one must be bigger one in the bottom, right? So we put an x to the third minus 3x plus 5. And again, what we get used to doing is on these ones, we're just going to ignore most of this function. And again, we don't ignore it when we're dealing with small numbers because those are all important. But when we got huge numbers, the only thing that really matters is the biggest parts. Again, so we're just going to look at 2x squared over 5x to the third. And yes, we can divide them out, cancel them out, however you want to think of. There's x squared on the top, takes care of 2 in the bottom, so there'll be 1 left. So we end up with 2 over 5x. And again, we just reason our way through here. As x gets bigger and bigger, becomes more and more positive infinity. What's infinity times 5? 5 times bigger than infinity. And you got this huge number in the bottom of a fraction. What's 2 divided by a very huge number? A very small number. So it's this practice we got as we looked at limits numerically. We could kind of see, well, as this gets, this is 2 divided by something really big. And it's going to go to 0. Okay, we got big enough, it's going to go to 0. It's closer and closer. So this is kind of just use our patterns. And that's one thing math is a lot about, is watching patterns. And if you're good in business, a lot of the business folks, they don't necessarily have to break it down to formulas and stuff. They watch patterns day after day after day. They internalize what's going on. When I was doing financial planning, one of our clients was, what did he have? He had a business over in Oregon. He had a plywood. He made plywood. But he got so good at buying and selling the makings for the plywood, sometimes he would make more money buying and selling the veneer than actually making it. So his shop sometimes was, they would say, well, we got nothing to do, because he would buy it and then he would sell it for more money rather than turn it into plywood. But he did it by just watching patterns. And it was a family business, so unfortunately his children didn't have that same knack. It was just something he had. He could just watch the market. He would know somehow, I should buy a bunch of veneer today, and in 2 days I should sell that veneer. And he was good at that. Okay. Patterns. Okay. So those are the 3 cases we get, and every one will fit into one of those 3 cases when we're talking about going to infinity. Okay. That kind of is going to wrap up what happens. They talk about something, they call it determinate forms. Let me get a new page. So if you read through the book, it'll talk about determinate forms. And that just means that they're kind of these models that we know what's going to happen. So if we end up with, the limit ends up being some kind of a constant divided by 0, that this is something that basically goes to infinity. When we divide by 0, instead of calling it undefined in calculus, we just start saying, well, that's infinity. That's one form of infinity. And if we've got a negative constant and we divide it by 0, where do you think we go? You got it. We go to negative infinity. Okay, so this is just kind of a general case thing. So we watch our pluses and minuses, and whatever that constant is, it doesn't matter if we divide by 0. Eventually we just say it's either going to go to plus or minus infinity. Another thing we picked up maybe with exponentials, if we've got some exponential with a base, a constant base, and we let the exponent go to infinity, what do you think we're going to get here? So we have 2 to the x. As x gets bigger and bigger and bigger, what's going to happen to the output value? It goes to infinity. Okay. We'll say equals. I guess equals is not really correct, but the limit, yeah, it's just going to keep getting bigger and bigger. However, this is a different one, something we could compare to. If we've got some constant and we raise it to the negative infinity. Does anyone remember what a negative exponent does? It's 1 over. It gives us a reciprocal. And so to analyze this, and this is one thing you want to get used to, because we'll start dealing with negative exponents. So this, we want to just think of this as 1 over k to the positive infinity. Okay. And we already talked about this. What is k to the infinity? Well, it's going to go to infinity. So we're starting to think of 1 over infinity. What is that going to 0. Exactly. So we just kind of talked about that. So when we got exponentials, we watch for those exponentials, and if the exponent goes to infinity, we're going to infinity. If it goes to negative infinity, though, we get a reciprocal, and then we go to 0. So with exponentials, we always shoot off either to infinity or to 0. Pretty much how it works. And that covers pretty much the determinate forms. They go into a little bit more detail, but this boils it pretty much down to what we've been talking about. It's just, think of it just as patterns. And we're just, in math, we're just trying to focus on what is the important part of this function. And when we go to infinity, it's just the big parts. When we're looking at limits close by, though, we do have to examine the whole thing. Okay. Questions? Okay, so I've gone into student view. Let's take a look and see. I think we can do this. So like this one, is it this x plus 1? Does anyone remember what we call that kind of a function? Remember the terminology? It's not open, it is closed form. Okay. Again, you don't have to know that, but that's in the book. This is a closed form function, which means it's continuous. So to evaluate the limit as x goes to 3 of x plus 1, what do we end up doing? Oops, that's not very good. Let's go with a darker color. We're just going to evaluate x plus 1, so we do a 3 plus 1. That should be 4. That's all we have to do. We can even try it. We put in the 4, submit our answer. We got our check mark. Okay, so be a few of these. I just want to look and see if we end up having any of the ones we have to factor. How about this one? Do we have to do any factoring here? Why don't we have to do anything special with this one? Because don't we have a problem at 0? Plug in 0, it's undefined. But why don't we have to worry about it? We're not using 0. Okay. If this question was the limit as x goes to 0, I think at this point we'd have to throw up our hands and say we can't do it because we actually don't have the tools yet for this one to find the limit as x goes to 0. But the limit as x goes to 3, it's a closed form function at that point. So again, we just plug in the 3, work it out. So we end up with 3 plus 3 over 3. That's all we have to do because it's closed form on its domain and 3 is in the domain. 0 would be the only problem. So we end up with 6 over 3, which gives us 2. We plug it in and we'll be good. Okay, so some of these are just, you know, that's all we're doing. But let's see if we've got, yeah. Okay. Yeah, yeah, so far just plug them in. So far we're good. Oh, this one's going to be tricky on some because it's actually so easy, but what's the problem with this one? Well, it's 4. There's no place to put the 3, and so it's a constant function. I think it's very simple, but it would always throw me off because I go, what do I do with this? There's no place to put the h, right? It's not 3h, but this one, it is just, the limit is always 4 for everything. It's a constant function. What's that? Yeah, that's what I said. So maybe we have to just keep going because I remember there being 1 or 2. Yeah, this one. So if you plug in 0 for h and h, you get 0 plus 0, you get 0 on the bottom, and you get 0 on the top. And again, whenever you get 0 over 0, that's called an indeterminate form. It really doesn't tell us anything. So this is one where we actually have to do a little bit of factoring. So let's go ahead and take a look at it. Again, when you go to do it, you'll probably get different problems. If not, well, then maybe ask for a different problem, because if you want some practice or just copy, you know. So what do we? How does this thing factor? Well, 3h squared doesn't factor, but there's a 4 and an h that can come out, so we do the 4h. And if we take 4h out of here, there's a 1 left. And if you take 4h out of here, there's an h left. So what does that allow us to do? Again, all algebraically stuff. This h can cancel with one of these. And so this gives us 3h over 4, 1 plus h. Now can we plug in 0? Because yes, because if we plug in 0, we don't get 0 on the bottom. We still get 0 on the top. That's okay. We can always take 0 and divide it by something, but we just can't divide by 0. So now's the time where we don't, okay, let me try this again. Plug in 0 for h, for the variable. 1 plus 0 is 1. 1 times 4 is 4, so I get 0 over 4. And now this is no longer indeterminate. It's 0, right? But see, when I had 0 over 0, I couldn't say that that was definitely going to give me 0. I don't know what it's going to give me. But now I know that the limit actually is 0. Does that make sense? Okay, so we had to algebraically do a little bit of factoring. Just to show you I've got nothing up my sleeves. We'll plug it in, because occasionally I'm wrong. And sometimes I go, oh, I forgot something. So I always like to check myself. Let's put it in. And we got it right. So it always feels good. Especially when you're up here in front of everybody else and they think you're supposed to be the expert. So we're paying this guy, you better be getting the right answers. And then you get a wrong answer. It doesn't feel very good, but I'll try not to do that too much. Okay. So far so good. Are we, yeah, that's getting nasty, right? But not too bad. You just, a common x comes out here. How many of you are passionate about factoring? Oh, no hands. Me neither. Okay, I'm with you. Okay, so we'll do a little bit. And again, I'll tell you, that's why I get these, usually factoring, we have to do it here. Later on, we get these methods that we don't have to worry too much about the factoring. So can someone help me with the bottom? What does the bottom become?
X plus 4.
Okay, so an x comes out, then we get an x plus 4. Good. And sometimes when you get the, and that's the simpler one, I'm going to guess that probably in the top x plus 4 is part of the factoring, because 32, I'm just going to put it up there, and I'm going to guess that one of the factors is going to be x plus 4, because that would make it nice, because that will cancel out, right? So what times 4 is 32? 8. So then I'd make the guess that this other one must be x plus 8. Let's see if that works. 8 times 4 is 32. X times x is x squared. And then we get this 4x plus 8x. 4 plus 8 is 12x. So it worked. Okay. So again, I don't expect any of you to really just get passionate about factoring, but it's there a little bit. And again, if you, most of these problems are set up, they're contrived, and that's the reason I don't spend too much on factoring, is they're a very special problem. Real world problems don't factor nicely. That's why we use the calculators for most of this stuff, and that's why we get these other techniques. You're not going to face, if you've got a nicely factoring polynomial, you're doing math from a math book. You're not solving world problems. If you're solving world problems, you need some more advanced mathematics and technical. So the x plus 4 cancels, and really we're left just taking x plus 8 over x. And now is it safe to let x become negative 4? Yeah. I guess I should have said it here, but if we let it be negative 4, we get 16 minus 16, and that gave us 0, so that's why we couldn't just plug it in. I guess we should try it because maybe it was okay. But now we take our negative 4, put it in for x, so negative 4 plus 8 over negative 4, and what do we get? 4 over negative 4, which gives us a negative 1. Okay, so there's a few of these, and I think this will be the last one we'll do. We'll take a look at, what is that, negative 1. And there it is. Submitted and works. Okay. So some others, I'll let you have some fun with those. Again, do we need to worry about factoring here? No, because x is going to infinity. So what do we do when x goes to infinity? Yeah. Don't worry about the small stuff. Yeah. Don't sweat the small stuff. Get rid of it. Just get the big terms and see what the ratio is, right?
So that's only with infinity?
Yes, only with infinity. So it's kind of like, that's what in math, you just watch the problems and then you know where to shift. Okay, this one is using this thing. It's going to infinity, so it's either, just look at the two biggest things. And again, it's going to be the ratio of 12 over 4, right? Because the x squareds will cancel. 12 divided by 4 is 3, so that's going to be the limit. So when x goes to infinity, it's going to go to 3. If you'd like, you could graph it, and what you'll see is as you go further and further out, the graph just keeps getting closer and closer to 3. The y value gets closer and closer to 3. You can see these things graphically. If you look at the table of values as x gets big, your y value is going to get closer and closer to 3. And eventually it'll just start saying 3, because it'll, it's so close to 3. But that's...
So on the calculator, do we just put how many learned in class, like y equals and
Yes.
that, or
You could actually put the whole thing in there.
how do you do a limit?
You don't.
Okay, no.
The limit is a conceptual thing. So then what you do, you go to the table and you look when x gets really, really big. You look at x as 1,000,000, x as 1,000,000,000. Just keep looking bigger.
So we
That's
just
how you...
put, whatever's next to it,
Yes.
and then like the graph, then we can see what it's doing.
Yes. So yeah, you could graph this as y1, and then either look at the graph will go to 3, or look at the table, and the y value will be going to 3. Hope. Gosh. Let me see. Not good. Not good. Okay. Okay, we're still streaming. Yeah, looks like it. Okay. All right. And again, there'll be a few more problems, but kind of see we're into the different ratios. Just look at the biggest ones, and that pretty much takes you through, except for this last one. And this is now an application problem, so you'll run across a few of these. So let's just take a look. Let's set this one up at least. Okay. So the cost of fighting crime is increasing steadily at period. Total spending on police and courts can be approximated by PFT. So this is what it costs in billions of dollars. Again, T between 2 years and 19 years. And then total spending on police and courts. So I guess P is for the spending on police, C is the spending on courts. This is where T is time in years since 1980. So this goes to what, 1999, 19 years after 1980. And then wants us to compute this limit as the time goes to infinity, the cost of the police over the cost of the courts. It's 2 decimal places and so forth. So what do we do to set this up? Well, if you just look up here, just to save ourselves some time, it's really just take these 2 functions and turn them into a ratio. So this one on top, this one on bottom. Okay. And what do we know about something as it goes to infinity? What do we need to examine? The highest degree. In this function, what's the highest degree? T to the first. It's not a very, they're both linear functions. Okay, and so you can see we cancel out the back part, cancel out the t's, and our ratio is just going to be 1.72 divided by 1.047. Do that math, and that goes here. In fact, let's just do that. So rounding to 2 decimal places, 1.64. I just hit enter. Scroll up a little bit. Yep, got a green check. Okay. Picture that. Oh, and then it's just this, if this trend continues, identify indefinitely the annual spending on police will be blank times the annual spending on courts. So this ratio actually tells us how much more it costs. So the 1.64 is actually the same answer there. I forgot to put it in, but go ahead and do that. Okay. But that's nice because we get another try, right? 1.64, because I want all the points. Why would I want all the points? I want to get all the points because Little Crow takes all those points and figures out a ratio or a percentage, and he multiplies that percentage times 20 points. If I have 100%, then I get all 20 points. If I don't have 100%, then I get a percentage of 20 points. So it might not be a big deal, but since you can in this homework get perfect scores, because if it's not right the first time, you have three tries on each one, and if it's not right after that, you just ask for another one anyway, and so you can get 100%. So there's a benefit in getting it. And there's a small enough problem bank, I think, that it's worth it to make sure that they're all correct. If you have a real issue with something, email me or something. If we can deal with it. But that's kind of how I do the grading. So if you've checked Canvas, I've updated those. I did it for 10.1 and 10.2 already. Okay. And I found a way I can basically just export this into an Excel spreadsheet and it updates. So I'll do pretty much weekly updates. I've got nothing else to do. I might do it more often than weekly, but I just put in an Excel spreadsheet and then send it over to Canvas. And it's a 15 or 20 minute process, but I'll do it if you need an update and such. But I'll try to do that at least weekly as we're going. If you got 100% here, every assignment's worth 20 points. If you did 1.1 and 1.3, those are the ones, if you just did a few problems even, I gave you 20 points for each of those. So if you haven't done those, hold them up and do a few. Do one at least. Okay, do at least one, and you get your, it's always nice to start off with 40 points of extra credit. Again, it's going to be based off of 1,000 points, so 20 points is like 2%, but when you get down to the end, maybe that 2% pushes you over a grade mark. I'm hoping that you're just so far beyond that it's, you're already at 102% or something, but whatever you need. All right. Anyone need a break? No? You're gonna make me keep going? You gonna drop them? No, we're fine. Because the next part would just, actually I'm just gonna pull up some of the problems. We're gonna take a look at them because really the next one is just slope. It's just finding the 2 points, the x and the y. Kind of like what we did, subtract the x's, subtract the y's, and then it's a ratio of the change in y over the change in x. Okay. So I didn't even look at the book, but I think you'll be fine. And again, remember at the end, always submit your assignments, I guess, when you are finally done. I guess I'll just save my progress. Of course, I'm not really a student in the class, so it probably doesn't matter. Okay. So I'll go back here. What we'll do is to take a look at 10.4. We'll take a look at a few examples. I'll get you on track, and then probably in about 15, 20, 25 minutes, we'll finish up, and that gives a good more than an hour left that you could work on any more of the assignments. If you're working ahead like some of you were last week, I'll just be honest, I haven't looked ahead myself, so we'll take a look and see what we're supposed to do in those sections, and I'll help you if you want to stay and do those. Okay, so this is average rate of change. Oops, what's happening? Oh, I need to be in the student view. Okay, so in the beginning, they give you some functions, and they want you to calculate the average rate of change over the given interval. So what does it mean to get the average rate of change over an interval? Do this. Get a little bit bigger. How's that? A little bit better. What's this interval mean?
Distance between 0 and 2.
If it was absolute value, that's what absolute value would possibly mean. Yeah, absolute value means distance from 0 to 2. In a way, you're right. It's yeah, because one end is 0, the other end is 2. But the 0 and 2 are the domain. They are our x values. So what they literally are, 0 is the x, the 2 is an x. Okay. And you're right, when we find the slope, we're going to find the difference of those, so that'll give us the distance between those two. That's the difference in the x. And then to find a rate of change, we need to also find the difference in the y's. Okay? So the way we might set this up is take the two sets of points. So 0, -3 from the function table, and then 2, 6. And again, if you want to use the slope formula, y2 minus y1 over x2 minus x1, you're welcome to do that. What I like to do is just line the points up, subtract the top from the bottom. So 0 subtract 2 gives us -2. -3 subtract 6, that should give us like -9. And then we take the x change, put it under the y change, and there's our answer. So -9 over -2, negative divided by a negative gives us a positive, and that's probably an appropriate answer. I think I was working with someone though, when it asks for, it said to give it like to 2 decimal places. That means it actually wants you to divide and write your answer as 4.5. Okay, so if you're not getting it right, and I think maybe someone emailed me. Does anyone remember? Was it? Anyway, I remember the fraction you were putting in was correct, but then we looked at it and it said round to 2 decimal places, so that's all we need, a decimal. Okay. Yes. The -3 came from down here, and I messed it up because I covered it over, right? So if we, yeah, so there it is. So I'm getting it right from the table of values. So basically, in every single, I think it's just about every problem in this, you're going to be given 2 x values, that's your interval, and you need to find the 2 y values. You'll either look them up in a table, or look them up on a graph, or you'll plug them into a function to get the y values. You'll take the 2 x values, plug them into the function, get those values. But the end result is you'll get 2 points, and you'll do this process to find slope. Okay. And again, if you like,
Let me try, because I think in one of the homeworks I put in decimal, and it showed it as wrong, and it showed me in fraction
I
form.
think, right, okay. So which one would you like me to put it in? Decimal or fraction?
We get 3 tries. So it
We get
doesn't
3
matter.
tries. Let's try 9 divided by 2. Submit our answer. Hey, it liked it.
Okay, so fraction form.
Yeah, so this fraction, so if it doesn't say anything, probably fraction form is what it's going to want.
I didn't think in the opening, like in the beginning class, it's like when it shows you how to input everything, it says put it in fraction form.
Okay, let's try 4.5. See if it, because sometimes it doesn't matter. So in this case, it doesn't. Yeah. So it gets a little bit less worried. But again, sometimes if it does say round it to certain decimal points, that's saying do the division. Okay. Here's another one, basically same thing. 2 x values, find the y values, find the slope. Okay. So far so good. Here's another one. Endpoints, that's that. There's y values, find the slope. Okay. And here we go. This is a little bit different. Calculate the average rate of change of the given function over the given interval. Okay, assume a equals, so we've got some values here. Again, we've got the intervals, but this time what we have to do is we're looking up our y values on a graph. And they give us some information here that a is 13, b is 16, and c is 19. This is how they randomize things, because they actually won't change the graph. If you ask for a new problem, they'll change the values of a, b, and c. Okay, so what do we need? Well, we need this point here. When x is 2, what is y? $16. And then we need the other endpoint, which is going to be x is 5. So we put 5 here. And when x is 5, what is y? Doesn't say. Well, if that's 19, let's see, 16, 17, 18, 19. Does that make sense that this would be 18? Okay, so conceptually what we're doing is we're finding the rate of change between these 2 points, which is going to be the slope of the line that connects the 2 points. Okay, it's not actually on the graph anymore, but we're taking those 2 points, finding that slope. And we're going to see that is what we're going to call the derivative. We're also going to call it a secant line, but it's just, 2 points. And what we do with the derivative is eventually we get those points, we start with 2 points, and then we bring them closer and closer together, and we see that the limit as we do that, that's really the derivative at a point. And that's what we'll do in 11. And that's when the mathematics actually becomes easier. So again, this is all this build up to it. But what we get is, if those were our 2 points, again, we subtract 2 minus 5 is -3. 16 minus 18, would you say, is that like -2? Take the x's, tuck it underneath the y's. And I tell you what, when I do it this way, I never make any problems, any errors. When I do the formula, y1 minus y2, I typically will make errors all over the place. I'll mess up with negatives, I'll do all sorts of things. When I do it this way, straight down, tuck it underneath, it's like, it's almost too easy. I go, wow, 2/3, so the negative, so it's going to be 2/3. And again, this one will be actually prettier if you just put it in as a fraction, because the decimal is going to be 0.666667 someplace. And then, okay, so that's, I think there's a couple of these where you actually just look it up on the graph. And then, yes, sir.
So that average rate of change could be seen as a secant line, as a secant?
Yes, it's also called a secant line. I don't know if we use it in, they use it in the scientific calculus, business calculus. I don't know that we ever really talk of it that way, but if you've had trig before, it's, yeah, that's that secant line. And there's a relationship, if you've had trig, to the secant and this line that this slope we get. And the tangent line has a relationship to tangent of slope of trigonometry. But again, it's only for really math nerd people like me sometimes. Okay, and then now we got to see, is that dollars per month, dollars per year, dollars, or dollars per day? Well, it's a rate, so it's always got to be per something. And so we have to look here. What's down here? These are months. So and these are dollars, so it must be dollars per month. The y values is dollars. So on the top is dollars, bottom is months. So it looks like $2 per month, per 3 months. And again, that's another part. That's actually dollars per month. That's an important part of this concept, is what is that rate? So this class is about finding that rate and then what does it mean. So let me take a picture. And then we'll submit. We got green showing, so that's a good sign. Another one, a couple of these to do. And then these ones, how are we going to find the y values here? Well, we're given a function, so we're going to have to plug those values into the function. And now, let's see if I'm going to switch my view. Let's see if this works. Spent 10 minutes setting this up, so let's see if it works. So we plug it in. We plug in the 2x squared plus 4. Oops. 2x squared. Get out of the exponent, plus 4. And again, it's maybe simple enough you could plug in the values for x and y. Maybe you could do it in your head. I always like to do it with the calculator because sometimes I make mistakes if I do it in my head. We could go to the table. Oops. If you're like me, I had you set up the table as auto. No, it's auto. Let's see. Set both of these as auto. And let's go ahead. Let's start at 0. And let's change by 1. Okay. And again, the class I'm after lecture, if you'd like to learn more tricks on using your calculator, I'd be happy to help you with that. If you're already proficient, that's great. So we're looking at -1. So when x is -1, y is 6. So I'm going to write that here. Of course, you can't see it right now, but when we come back to the screen, it'll already be here. And then the other one we wanted was what happens when x is 3. When x is 3, y is 22. Okay, so we had to step aside. We did that. Now let's come back to our main window. And you'll notice magically the 6 and the 22 are there. We just need to find this slope, this rate of change. Okay. So again, subtract the x coordinates, subtract the y coordinates, tuck the x under the y, and you've got slope. Do the division, and we're good. So looks like we get -1 minus 3, -4, 6, subtract 22. Any help there? Is that about right? That's good because those are nice numbers to work with. Take the -4, tuck it underneath the -16. And again, this visual way of doing mathematics, it just, you get these patterns, you get quicker at it, and you get accurate. Negative become positive. 16 divided by 4 is 4, so our answer is just 4. Okay. But again, all of this is, we're picking out 2 x values, plug them into the function, look them up on the table, look them up on a graph to get those y values. Once you get 2 points, just find the slope. That's all this whole section's about. I think we'll keep going to make sure that I didn't miss something. Okay, so again, you plug the 4 in here. We okay, or you want to check that one? Starting to trust me, huh? This is dangerous. Okay, but we'll let the online community figure that one out. Okay, I feel pretty good about it too. Okay, and I think most of them, here again, here's another function, just plug it in, get the y values. Here we're starting to get at, what are we trying to do here? Do you think we should look at this one? Yeah, unfortunately you do. Okay, so this is what is building us towards what we'll do in like 10.5 and 10.6. So this is actually going to look at the derivative. So what we're going to do is we're going to take, they're giving us, notice, one endpoint, a equals 0. So we have one endpoint, 0, that. And then we're going to have another endpoint, and again, what we're going to start off with is we're going to start it at 1. We're going to find that y value. We're going to find the slope there. And then we're going to use this sort of limit thing. We're going to keep moving that point. Notice how the h gets a little bit smaller. Let's see, what is h? Wait, sorry. I jumped a little bit. The interval is, oops. The interval is from a to a plus h. Okay, so how I got this 1, since a is 0, 0 plus 1 is 1. So but if a was something other than 1, it wouldn't just be h. So that's the first one I'm going to do. And then I'm going to do it again, but now h is going to be 0.1. So what I'm going to be looking at is the point is 0. So this point doesn't change. But notice I'm taking the other point, and what am I doing? I'm moving it closer to 0. And each time I get a little bit closer to 0. So this is getting back to the concept of limit. And what we're just going to basically see is that we get closer and closer to a different value. Okay. In this case, remember, we're talking about a slope of a line. And depending upon what that function looks like, and does anyone know what 27x squared looks like? What kind of a graph is that going to be? X parabola. So it's going to be a fairly steep parabola because it's got a 27 in front. So it's going to look something like, I don't know, probably steeper than that. But notice as we move this point, if this is 0 and this is 1, we're going to get closer and closer. And so that secant line is going to get less and less steep. Okay, it's going to come closer and closer to a horizontal line. And what's the slope of a horizontal line? 0. Good. So in this, the details are, you're going to calculate the slope a lot of times here. So you're going to get this. We'll do this one. Plug in 0. We won't use the calculator. 0 for x, we get 0. Plug in 1 for x, what do you get? 27. So the first slope you're going to calculate, 0 minus 1, is negative 1. 0 minus 27, negative 27. Take the 1, tuck it underneath, you get a slope of 27. That's a pretty steep slope, right? Okay. Do it with 0.1, and again I'll go over here. 0 is always going to be 0, but plug in 0.1. 0.1 squared, 0.01, right? Because 0.1 times 0.1, 2 powers of 10, so it's going to be 0.01. So you're going to get, or just do this. I think if you plug that in, you'll see you'll get 2.7. While I do this, maybe someone should check me on that, because these are the types of things where I jump to a conclusion. I think I'm pretty good. Am I right? Anyone? You're going to trust 2.7. So if you take 27 times 0.1 raised to the 2, I think the answer should be 2.7. I'm asking someone to check me. If your teacher's not confident.
Oh, wait,
Oh.
no.
That's wrong?
I think, 'cause I heard it
0.27 maybe. I think, wait, 0.07, you need to move it 2 places. See, this is why I'm just kind of, I think it should be 0.27. That's my guess now.
I'm sorry, can you say it one more time?
So take 0.1 to the second power. So that's 0.2, that's what I was thinking. Okay, and then multiply by 27. Because 0.1 times 0.1 should give you 0.01. Move the decimal over 2 places. Yeah, this is what I'm talking about. I get a little nervous up here and then I blow it. But doesn't it make you feel a little bit more confident? Not really, but okay. So again, we do the subtraction, 0 minus 0.1. So what we're going to get is at this point, this one came up with a slope of 27. This is going to be negative 0.1. This is going to be negative 0.27. Take 0.1, put it here. And this is what the negative and negative cancel. So you're going to find that it now has a slope 2.7. Or did someone check? 0.27 divided by 0.1. I think a power of 10. I think you should get 2.7. I think that's what I was. Yeah. Okay. Yeah. 0.27. So notice our slope is already, we came down from 1 to 0.1.
0.27 divided by 1 is 0.27.
Right. Good. So we went from a slope of 27 to a slope of 2.7. Okay.
Wait, how come 0.1 is 2.7? Isn't it 2.27?
No, the slope, because what we're putting in here is the slope. So when h is 0.1, the slope, or the average rate of change that we calculated over here is 2.7. Okay. So notice that's what those are. And we just keep doing it again and again, and you can see it's going to get smaller and smaller and smaller. And it's tedious, but we don't have you do it too many times, but we want you to kind of manually prove it to yourself that that's what's going to happen. And so what you're going to, and the whole thing of this is you're going to see quickly when we have a minimum value. So we've got the bottom of a valley like that on a parabola. We're going to get a slope or a derivative of 0. We're going to see the same thing happens at the top. If it was a maximum, maximums also give us a derivative of 0 because that's where the slope becomes horizontal. Okay. You'll do a few of these types of problems, and you'll not have a lot of fun with them because they're just tedious to go through step by step. And it's really what this is like 5 problems. But I think you'll start to notice a pattern, and I think I'm just going to take a wild leap here. I'm going to enter, actually maybe I should first erase these knowing that what they are. I'm going to guess that it's like, well, we know this first one is 27. This next one was 2.7. So does anyone have a prediction for what this must be? Either 0.27 or 0.02. I think you're right. So if that's that one, what do you think this one's going to be? Okay. So see, sometimes you just find your way around, and this must be 0.0027. And hopefully we're right. We might be wrong, but I think we're on track. I haven't done this. Okay. So it wasn't as tedious once you start to see these patterns. And that's what, if you can do this with math, you can start to see, okay, that's what's happening. But do a further, the first few steps, and all it is here's an x, plug it into a function to get the y value. Here's another x, plug it in, and then get the slope. Okay, that's all this whole thing is about. But it's going to build up. The slope is the derivative. And we're going to find funky ways or nice fast ways to get different derivatives really quick just by doing it. And this is kind of going to give us a basis to say, yeah, it works. Okay, because when I get to a minimum point, this little parabola here, it makes sense that the derivative there, the slope at a point would be about 0. Okay, and let's see, let me back up here. Save that, and yeah, we'll just keep moving. I think we're pretty good. There's some. I think you should be able to handle these. A little bit of problem solving in different endpoints, so you're going to see different rates of change for different endpoints. Just referring back to the same table of values, though. And here's a graph. Again, a little bit more problem solving stuff to it. But again, you're just finding x's and y's, 2 points, find the slope between those 2 points, and kind of interpret what it means. I think, yeah, this one, again, there's this funky formula up here. Plug in the values. They give you an assumption. So this point is kind of easy to find because they tell you exactly what it is. But you should also be able to find it if you plug it in here. And then you've got another point that you're going to need to use the formula, find it, find the slope between those 2 points, and you've got your answer. And then if something was going down, what kind of a slope would it have? Negative. Okay. If it's going up, what kind of slope should it have? Positive. Okay, perfect. And again, a lot of times it's nice when you have the graph, you can visualize the 2 points and you can see whether it's going up or down. And that helps check your math, your arithmetic to make sure, well, it's going down, I better get a negative answer. If I didn't, I must have blown it somewhere. So you go back, you check your work. If it's going up, I better get a positive answer. If I don't, check my work, I probably dropped off a negative somewhere, did something wrong, okay? And that's all there is to it, okay? So tonight, we're taking advantage of knowing that we've got functions that are continuous, and we're looking at basically being able to do the limits algebraically by either plugging them in, or if we're going to infinity, looking what happens at the far extremes by just looking at the biggest biggest order of polynomial. And then in this one, it's just a slope, slope, slope. So to get slope, I need 2 points. I need an x and a y. The interval gives me my 2 x endpoints, and I take those and I've got to find the y values one way or another. I either have to look them up in a table, look them up in a graph, put them in a function. Once I've got them, it's just y equals, or m equals y2 minus y1 over x2 minus x1. Or just line up the points, subtract them, tuck them underneath, and get your ratio. You want there's a regression feature in the calculator. If you just want to plug the 2 points in and use that, you can get it that way too. However you want to do it, it's just do a fraction. Do a few problems, you'll get the concepts down, and then what we do is on Thursday we're going to finish off 10, which is 10.5 and 10.6, and that will be the end of our theory part of the course. And then what we do is in 11 we do the same thing again, but we do it easier because we find the little shortcuts that get us to our answer a little bit quicker without all the details of having to graph everything. But we're going to build on this theory. So it's kind of nice. You get a look at what we've done in the first part, but with easier techniques. And so it kind of builds on itself. Any questions? Good. Feeling good? Not too fast, not too slow? It's okay? Okay, good. So that's all I have for tonight. We've got a good full hour if you want to hang out and work on things. If you want to take off and work on it later, that's fine too. I will put this link, and what was our word of the day? Gregarious. If you can give me a definition on that, we'll a couple extra. Social? Sociable. Okay, that's why I don't know it. I'm not very sociable. Okay, so very good. Have a wonderful couple days, and see you back again on Thursday.
Was there a word?
Gregarious.
Gregarious?
Gregarious. And it is. I spelled it Gregarious.
Was there a quiz for the other class?
There wasn't because the video didn't come through, so I just we'll do a pass.
What was that word of the day for Thursday?
It was cool, but I didn't do a video. Well, the video didn't save, so I didn't do a word of the day thing. So,
Thank you.
thank you. Okay, so we'll say goodbye to the online folks. We're going to stop streaming. Hopefully we were streaming on.